All right, so here we are ready to go for more acids and bases. So the first place we'll start is talking about Ka, Kb, Kw, and the relationship between these three, because it's kind of important to be able to talk about how they are related to each other. So let's start by talking about this reaction here, right? And so clearly this is an acid reaction, right? We have an acid here, and over here we have the conjugate base, and we have a proton. Right, so that's definitely what tells us that that is a acid reaction, right? So here is our acid reaction. And so this substance will have some sort of Ka, right? And we can write an expression for this equilibrium, right? Where we have our products, right? Our proton and conjugate base over our acid. Now let's say we have this other reaction, which in this case is a base reaction. And how we know it is a base reaction is that we have a substance that is reacting with water, right? And it's forming a conjugate acid. And it's forming hydroxide, right? Which is, well, that hydroxide there is getting a little crazy. Okay, so it's forming hydroxide, which is a really good indication that this is a base reaction, right? We have something reacting with water, it's forming a conjugate acid and hydroxide, right? So that's how we know that. We can also write an equilibrium expression for this, but in this case, right, because we're dealing with a base, we have a Kb instead of a Ka, in which now we have a concentration of conjugate acid and our hydroxide over the concentration of our base. Right, let me clean this up here a little bit. Now, if you recall what we did with equilibrium expressions and the equilibrium constants that we worked with, if we are able to, right, combine these two equations, right, like here, we can combine these two equations, just like adding two equations in mathematics, right? We cross things out on either side of the equal sign, or in this case, arrow, right? We can cross out NH4 and NH4. Those appear on both sides. NH3 and H3 appear on both sides. And we are left with an equation that should look familiar, all right? This is the equation for the autoionization of water right here. And if you recall, there is an equilibrium constant associated with this, and that is, of course, Kw. Now, if you think back to when we talked about equilibrium expressions, if you have two chemical equations that you can combine to make a new chemical equation, then you can find the equilibrium constant for this new chemical equation by multiplying the two equilibrium constants that went into making the new one, right? So that will give you the equilibrium constant of your new reaction, right? It works the exact same way here with Ka and Kb, right, being our equilibrium constants for acids and bases. When we have our two equations that we combine to get the autoionization of water equation, right, we could calculate the equilibrium constant, right, for our autoionization of water from multiplying those two together. Right, this also means that if we are given, let's say, a Kb for a reaction, but we want to put it in terms of pH and not in terms of pOH, right? We can figure out Ka's for this because we could say Kw divided by Ka equals Kb, right? Likewise, we can say that, oh, sorry, if we want to put something in terms of base, right? I'm getting things backwards. If we want to put things in terms of acid and Ka, right, we could say that Kw divided by Kb is equal to Ka. Right, so this is a way that we can interchange between Ka and Kb given information that we have. And just as a reminder, right, Ka is talking about our acid dissociation constant, Kb is talking about base dissociation constant, and a little reminder here, or not reminder because I think this is new, I don't think I talked about this in the last video, but I'll draw a bunch of arrows here to remind us that Kb is always referring to a chemical reaction where a base reacts with water to form hydroxide and the conjugate acid. All right, so whenever you see a reaction like this, that is a base reaction, and you can utilize Kb when you are looking at the equilibrium calculations for anything dealing with that reaction. Okay, so now pH of strong acids versus pH of weak acids. So a reminder that pH, right, that is the negative log of the concentration of hydrogen anytime you're talking about that. And so for this kind of equation, right, where we have an equilibrium of our acid dissociating into a proton and our conjugate base, right, we have some sort of equilibrium. Now, for a strong acid, because the pKa is so large and the equilibrium lies so far to the right, we assume that all of it dissociates and that you don't actually treat this like an equilibrium, right? Because we could write an equilibrium statement for this equation over here. But if we have a strong acid, that's not going to be the case, right? We can treat it as going all the way to our product side. And so we do not write an equilibrium expression for strong acids. Right? To calculate the pH of our strong acids, we simply put in the concentration of our acid, right, and not our hydrogen, because with a strong acid, again, we can assume that this goes all the way to the right and that 100% of our acid will dissociate, so the concentration of our initial acid becomes the concentration of hydrogen ions when in solution. Easy enough. However, if we have a weak acid, right, so hydrocyanic acid, weak acid, things are a little different, right, because we cannot assume that everything goes to ionization, right? It does not completely ionize. And actually, this should be Cn minus, not OH minus. Okay, so if we are given this equation and we are given the Ka, right, we know what's coming next. We are going to write an ice table. Okay, so in this equation where we're trying to find the pH of this acid, right, pH question mark, I will give you that we initially have 0.2 molar of this, right? And if we have 0.2 molar of that initially, we have 0 of this. We are going to react, right, or that acid is going to dissociate, at least partially, right? So because these are all ones here, right, for our balancing numbers. 1, 1, 1. We don't have to multiply our changes by anything. So we can just say we are going to lose some amount x of our acid, and we are going to gain some amount x of our proton and our conjugate base. And so that means at equilibrium, there will be a value of x for each of the proton and conjugate base, and that we will have 0.2 minus x for the concentration of our acid. So now if we write this out, right, we write our equilibrium expression, we put some numbers in there where we have Ka is equal to x times x over 0.2 minus x, and that's equal to the Ka, right? We can simplify this to x times x over 0.20. Now, you might ask, that's not the simplification I was thinking. What did you do there? So now, looking at this, right, we can look at this number and say, this is really small, right? 10 to the negative 10 is a really small number, which means very little of this acid is going to dissociate, which means x, in turn, is going to be very small, which means compared to the amount here, this is not going to change. So we can just make an assumption that makes our calculation a lot easier, that x is so small, it is not going to change the amount of our original acid that's in there. So now our equation becomes x squared over 0.2 equals 4.9 times 10 to the negative 10, right? Because we made that assumption that because the Ka is so small, x is going to be so small that we can disregard it in this calculation. All right, so now multiplying both sides by 0.20, we get something that looks like this, right, where x squared equals 0.2 times 4.9 times 10 to the negative 10. We simplify that even further, right, and we get x is equal to the square root of 0.98 times 10 to the negative 10, which equals 9.9 times 10 to the negative 6 molar. Now that's x, which is both the value here and here, right? And if you did subtract 9.9 times 10 to the negative 6 from 0.2, you would see that this number, right, while it'll be like 1.999999 something, right, that's going to round up to 0.2. This is essentially going to be unchanged, and so we can make that assumption. So at this point, we have our value for x, which means that we have a value for the concentration of hydrogen. We plug that into our equation for pH. We take the negative log of the concentration, and we see that this will have a pH of 5. So note, right, this little note at the bottom. If the value of x is 5% or greater of the original concentration, the assumption that we made here is not valid, and you must use the quadratic equation, right? So like if this value of x had been 5% or greater of our original value, right, 2 or 0.20, then we could not have made that assumption. But because this value is much less than 5% of this, our assumption is valid. We do not have to go back and calculate using the quadratic equation. Okay, so now let's talk about the next thing on the list, percent ionization. So this is exactly what it sounds like, a calculation comparing the concentration of hydrogen ions at equilibrium to the initial concentration of our acidic compound. So here is it in equation form. If you really like that sort of thing, where percent ionization is equal to, right, our concentration of hydrogen ions at equilibrium divided by our initial concentration of our acid times 100%. I'm not going to go through a example calculation in this video because I am going to assume that you can work out this calculation on your own. Okay, on to polyprotic acids. So what polyprotic acids are? They are acids that contain more than one acidic proton that can be donated, right? Some examples are sulfuric acid, H2SO4, right? Carbonic acid, H2CO3. Phosphoric acid, H3PO4, right? All of these are polyprotic acids, right? Here we have 2 protons, here 2 protons, here 3 protons, right? And so just like with monoprotic acids, we are going to have some Ka value, right? Each acidic hydrogen or proton is going to have its own Ka value, right? So for something like H2SO4, we would have a Ka1 and a Ka2, right? That would correspond to the reactions of H2SO4 forming H plus and SO4 minus, and then a second Ka value that would be for the reaction of HSO4 minus in equilibrium with H plus and SO4 minus 2, right? So that would be how we would define our 2 Kas. They would be Kas for separate dissociation equilibrium here. It would look like that, and that's how the Kas work for all polyprotic acids. So as it says here, generally only the first proton is significantly acidic for any polyprotic acid, and so for the vast majority of them, only Ka1 is relevant for calculating pH. Right, so most times the only one you're going to use is Ka1. And then also, according to your book, if the Ka values for a polyprotic acid differ by a factor of 10 to the third or more, the second and third protons do not contribute significantly and can be ignored when calculating pH. And like I said, for the vast majority of polyprotic acids, they differ by a factor of 10 to the third or more, meaning that we don't care about that second proton or third proton that is coming off the polyprotic acid. So, right, we can ignore our Ka values except for Ka1 in most instances until we start talking about buffer systems, in which case we're going to be more concerned with Kas that are not Ka1. But we'll get there when we get there. Okay, so now is a good time to talk a little bit about acid and base strength again. And we'll start off by talking about how Ka and pKa, right? Remembering that pKa is equal to the negative log of Ka, right? And pKb is equal to the negative log of P of Kb. And you can use these numbers to estimate the strength of weak acids and bases. All right, so a large Ka or Kb indicates a stronger acid or base, right? Because like if we have a value of, 2 times 10 to the negative 3, right? That's going to mean that a significant amount of our acid is going to dissociate. Whereas if we have a Ka value of something like 2 times 10 to the negative 11, right? That's a really small number. The vast majority of our acid is not going to dissociate, and so it's not going to be a strong acid or base, right? The opposite is true with pKa and Kb, right? Small pKa and pKb indicate stronger acid and base, right? Because remember that pKa is a logarithmic scale. So, right, when you take the negative log of something like 2 times 10 to the negative third, or sorry, 1, we'll just go with 1 since that's easier for me to do it in my head, right? The negative log of 1 times 10 to the negative third is 3, right? Whereas negative log of, let's say, 1 times 10 to the negative 11, right, is going to be 11. And so, as you can see, right, the larger the number that we put into this pKa equation, the smaller the number we get out the other side, right? So low or small pKa indicates a strong acid. Large pKa indicates a weaker acid. So another thing that we have to keep in mind when we talk about acid, base, and strength is talking about the strength and polarity of the hydrogen acid bond, right? Where highly polar HA bonds tend to be more acidic, right? Because in this case, if we have a highly polar HA bond, right, most of the electron density is being pulled over here to the A, which means that this, having not a lot of electron density, can easily leave. Right? The other thing is bond strength, because if the HA bond is very strong, right, like there is a lot of strength in this bond, right, they want to stay together, then it is much less likely that the H will leave, right? If there is a strong bond here, the H is going to want to stay with the acid and be less likely to leave. The other thing we have to take into consideration is conjugate acid or base stability. So the more stable your conjugate base is, means the weaker the acid is going to be. Or, sorry. Oh my God, I apologize. The more stable your base is, which means the more stable your conjugate base, the easier it wants to hang out without the hydrogen on its own, so the stronger your acid is going to be, right? So more stable conjugate base means stronger acid because the base will be okay hanging out on its own without the hydrogen. And then weak conjugate bases are made from strong acids, right? So if you have a very weak conjugate base, right, like you look up and your Kb is a very small value for your conjugate base, that means that the acid that was made from is very strong, right? And so the opposite is true, right? Unstable conjugate bases have weak acids, and strong conjugate bases are made from weak acids, right? So the opposite of this rule is true. And so the last thing that we're going to talk about here deals with the structure of your acids and bases, particularly compounds involving oxygen, right? So the classic example of this is the chlorites and chlorates bases or acids, where you have something that looks like this for hypochlorous acid, right? Something that looks like this for chlorous acid, something that looks like this for chloric acid, and then we get to perchloric acid, where you have something that looks like this, right? And this is the weakest, this is weak, this is strong, and this is strongest. And so why that is, right? So if you look at this one, once these electrons come back into the system, right, and H leaves, there's not a lot of place for those electrons to go, right? They're just kind of hanging out there. This is not particularly stable on its own and doesn't really have any place to put those electrons. So the hydrogen in this case is not likely to leave. The other thing is, right, there's not as much stuff over here pulling electron density, right? It just isn't pulling as much. When we get to this one, right, here, if the electrons move and the H goes to leave, there's more places for those electrons to go, right? They have more place to go. They can spread out among more bonds. And two, there's more electronegativity and electron density being pulled in this molecule, right? This is more polar, and so the H is going to be more likely to leave. Right? We get down here, and again, we're increasing the pull on those electrons. We're giving those electrons more places to exist, and so the hydrogen is more likely to leave. And then by the time we get to here, right, with our perchloric acid, there is a lot of highly electronegative stuff pulling on these electrons, right, which means there's not much electron density on the hydrogen, and these electrons have a lot more places to go, which means this H is going to be very likely to leave. All right, this conjugate base is very stable, meaning that the hydrogen is going to leave because this conjugate base doesn't really care whether it has that hydrogen or not. In fact, it might prefer to not have that hydrogen anymore. It kind of wants to get rid of it to have those electrons to do whatever it wants with. So that is the talk about acid-base strength involving structure, particularly compounds involving oxygen. Okay, so that's it. The next time we will start to talk about more acid-base equilibrium, particularly involving titrations, and so adjusting the pH because we are reacting things, some solubility, and of course, everybody's favorite, buffer systems. So I'll see you in class.